Good morning, internets. Today's topic is something I term as boundary layer physics. This is what I what I picture when you get into boundaries of things. So, why does boundary layer physics? Okay, and that's what happens at the layers of things. When you get to a door, you have to open the door to go in and out. The door restricts airflows. So that's, a minor change in boundaries, just as a loose example. I'll do a little bit more on it. But now, why this is matter? So, recently, a lot of articles about discovering the Earth's atmosphere extended beyond the moon. We can see particles from Earth's atmosphere beyond the moon because there never was a hard physical boundary there. It's a very graduated sorting of elements using gravity. Some of those just have an escape velocity. They're headed out in that direction. It could take them another million years to move further in or out. But all those little particles are there, and they're dispersed among the gravity or the vacuum of space. It's a relative vacuum, remember. So if you're already in it, it's not a vacuum. It's just what it is. So what happened was we learned, and we got a measurement instrument far enough out that we found what we expected to be there. So that I know, those particles were expected to be there. That's why we went looking for them, to verify what we understood, not to prove something else was wrong. Because that's the subtleness of gravity and time and huge physics. The gravity of a planet versus the whatever an atom's going to do. Let's call it buoyancy. So when you put it all together, you've gotten into vector physics. So there's math that describes these things in very gross, soft, squishy terms. But it has, the study has pretty tight error bands. So we know what we're doing is heading towards the right thing. So that is a boundary layer. Our atmosphere is the boundary between us and death. So it behooves us to understand what this atmosphere is and how it works and what it means. So we said there's atmosphere out by the moon, but there is so little of it in the volume of space, there really is no way for us to recover it. It doesn't do us anything. We can't breathe it. We can't harvest it. It simply is too dispersed. So you can get into looking, if you like some of the information in periodic tables, there is atomic abundance numbers that give you some hints or ideas how much of something is in something. So we have abundancy numbers for iron on the Earth. Almost all the iron is in the Earth, bound on the ground, because it's heavy. But there is some small amount of iron in the air, because dust travels. We know it does. As example, Europe gets a lot of dust from Asia and the Middle East. Those dust storms they have kick up and are mapped across the planet by satellites, and it settles, and it's a problem. The dust is actually enough to be a problem when it does precipitate out in cities in Sweden, for instance. So this is travel. This is atmospheric transport rules So the atmosphere can deposit, atmospheric deposition. The atmosphere can also release. So if something can get thrown up high enough in the atmosphere, it's going to escape our gravity, or it can escape our gravity, or there is enough physics going on for it to just stay out there in space until maybe a wave is made that pushes it somewhere else. So you can go into things like, would a gravity wave affect whatever we're talking about, that dust in space? And the answer is yes. Yes. So this boundary layer physics idea, if you go look at a wall, when you run into a wall and your nose starts to bleed, you've hit a hard boundary. But that wall at its softest, when you get to it with microscopes and physics and other measurement tools beyond what our physical senses can see, you might find it's flaking and dusting and chipping, and you could actually measure how it's flaking because of corrosion, oxidation, or being swept. Or so you could go learn something about that paint barrier between the atmosphere and your sheetrock. Now these seem kind of silly examples, but these have been gone over. So another example of boundary layer physics is a vacuum chamber. People talk about getting to an absolute zero pressure. So 0 bars of pressure, 0 atmosphere would be. Absolute zero is another conversation, but you can't get there. So as soon as you get that chamber evacuated down to some certain level of, there's only this many atoms left in that chamber, if you walk away from it and come back, metal ions from the walls of the chamber, from the glass, from the pressure gauge you're trying to measure it, at a subatomic level, particles dissociate. There is this thing called vapor pressure. So anything, when you start to get close to the vapor pressure of any elements or compounds, you're going to draw them out of materials. So this is why absolute zero is hard to achieve. We actually couldn't pump some equipment down as far as would be nice because there was electronics inside that would outgas, and you would destroy the boards, or the chips that are on the boards. So people think of these things, but typically you don't worry about boundary layers. You do mass flows, you do a pipe flow, total flow through a pipe, but physically in that pipe the gases separate out so that the gas at the center of that pipe is not the same constituency as the gas at the outer edge of that pipe. If it's moving, even if it's not moving, there can be some things going on. So if you have to think about these things, you need to know how to think about these things, but you don't concern yourself about boundary layer physics necessarily. Yet you'll watch a coffee pot boil water, and those huge bubbles that come off the heating element are hard to explain, but they're thermal expansion properties of oxygen in the water and the boundary of that the heated element and the cold water. So at that little tiny microscopic boundary, there is fluid dynamics and a bit of chaos going on that can be described well. And then you throw in something like neutron bombardment into that microsurface, and you start to know about nuclear reactors and the side effects of radiation on other materials, and that neutron bombardment will destroy metal over time. Or ion migration, where elements leach into or sink into other elements, means that material becomes contaminated, and that's a crystalline structure kind of thing. And there's still radioactive elements that have leached into the metal or been made in the metal. Neutron bombardment. Remember, we've got a bunch of high power particles running around that do things. We prove it stochastically. So there you go. Intro to boundary layer physics, or at least where you have to start considering it. We went to space, we went to a vacuum chamber, and when you get to boundary layer physics, you get into things like, ionization potentials. Where do photons and atoms go and come from? And you're almost at the atomic level, or subatomic level, but not quite. So those subatomic interactions are a weight of X on anything you think about, and they can throw what we think is chaos into a system when it's just something that is not worth worrying about. Maybe, in the normal world without this excess radioactivity, that piece of metal was going to last 10,000 years before it rusted away. Now it's going to last 5,000 years, and it's going to crumble away and rust away. So that's subtle, but that your grandkids might be in that building. So hey, there is why boundary layer physics is more amazing than beliefs.